I'm just going to start recording now. Is it recording? It is. Okay, dope. All right. Close all that stuff out. This is the first picture we have to look at. Okay. Yeah, all you do is start. Okay. This is our code. This is how we generated all of the plots. We imported all the necessary libraries. We set our sample rate to 10 megahertz, and then these are the center frequencies we chose, which we'll go through when we look at the spectrograms. This center frequency would change depending on each signal that we're looking at. These lines basically connect to the SDR Pluto. Then it sets the sample rate using this parameter up here. Then we set the bandwidth, which is also going to be 10 megahertz. Then the local oscillator is set to the center frequency, which we set based on which frequency we're looking at. The buffer size was always 1024, and that would change the window sizing in time, but we didn't want to change that too much, so we're getting good data. Then we take what's on the buffer and put it onto this data array, print the data array, and yeah.
And then we are using signal spectrogram to get the sample frequency F, and then T, which is an array of segment times, and then we want to return two-sided arrays. So we set the return one side to false, and then because F is the sample frequency, we want to add it to center frequency, which we set before. And then we are using the matplotlab.p color match to plot the spectrogram. And then we first set the corners to T, and then the FFT shifts of F. And then we set the parameter which the 2D array which we want to color map to FFT shifts, and then SXX, which is the spectrogram of X, which is the spectrogram of the data. And then we select the shading style to go row. And then we set the X label and Y label as below, and then we let the plot to show.
As for the physical layer characteristics, an example of one of our results is on the left. So the blue would be the lowest energy noise floor, and then the yellow would be the highest energy. So we used the towers to look at, then we looked at the frequency band, the AWS frequency band, and that's how we got the center frequency that's predicted. And so we'll walk over the 5 graphs now.
So the way we found each of these center frequencies was looking on Cell Mapper, and it will give you the uplink and downlink frequencies for each cell, and we use this tower located right next to WPI at the Trinity Lutheran Church. Then we chose for the first cell, we chose both its uplink and downlink frequencies. And basically, we just did that for corresponding cells on the tower because our spectrograms were working really nice with this specific signal because they're strong and right next to us. And we had some pretty nice spectrograms set up. The best one was not this one exactly, but there's one more. Yeah, the downlink for the cell 1. Which had a center frequency of 782 megahertz. And as you can see, we pretty much got exactly what we wanted for that spectrogram. And yeah, that's it. Honestly,